Hello everyone. We are starting our session within 5 minutes. Vice Chancellor Madam is joining soon. So once she will join, we will start our session. Be with us. Shortly we are starting with the session. Thank you.
Madam, good morning. Hello.
Hello, good morning.
Madam, good morning. Madam, within 1-2 minutes, we'll start the program.
Yes, fine. Not an issue.
Welcome you,
Thank you so much.
Sir, Padge Madam.
Yes, sir.
Yeah, we'll begin the program.
Yes, sir. We will start. Yeah, sure. Hello, everyone. Namaste. I am Dr. Rajashri. A very warm and cheerful morning to all, with a great joy and immense exultation. Chief guest of our today's program, Honorable Dr. Mrinalini Fadnavis Madam, Vice Chancellor, Punyashlok Ahilya Devi Holkar, Solapur University, Solapur. Guest of honor, Honorable Dr. B. Surendranath Reddy, Principal, Honorable Dr. K.J. Karande, Convener of the program, Professor Anil Nikam, all resource persons, HODs, faculty members, and Indian as well as foreign participants. I feel privileged to extend my warm welcome to all presented here for for 1 week faculty development program on essential mathematics for engineers and researchers organized by Department of General Science and Engineering of SPN Sinhagar College of Engineering, Koti, Pandharpur. We begin this program by the mercy of Mother Saraswati and Lord Vitthal. Here at Sinhagar, we not only value the academics but also cultivate our creative tendencies through research work. As we all know, scientific research is one of the most exciting and rewarding of occupations. So to boost the interest of researcher and to take them familiar with latest mathematical tools and techniques available for research in engineers and other fields of research, we have organized 1 week faculty development program. I now request convener of the program, Mr. S.V. Pawar sir, to please give a brief introduction of the program. So please.
Hi and good morning to all. I am Professor Shivaji Pawar, convener of the Faculty Development Program, Essential Mathematics for Engineers and Researchers. The FDP will be conducted from 23rd of November to 27th of November 2020. Since mathematics is a structural background of all engineering subjects and plays vital role in other sciences, the FDP intend to make participants familiar with latest mathematical tools and techniques available for engineering research. With this, to get basic understanding of mathematical concepts which are useful in the field of engineering, and also to understand the recent development in mathematical sciences. For this FDP, near about more than 400 participants have participated, out of which 5 participants are from out of India, 170 plus participants are from out of Maharashtra, and 220 plus participants are from Maharashtra. So during this FDP, total 12 sessions will be there, and all sessions are conducted by the renowned faculties from NITs, universities, and reputed institutes. Apart from this, few sessions will be conducted by the faculties of host institute, in their respective research areas. So this is what the outline of FDP. With this, I am concluding a brief introduction of FDP. Thank you.
Thank you, sir. Now I would request our principal, the most dynamic and versatile personality and inspiration to all of us, Honorable Dr. K.J. Karande, sir, to please address the gathering. Please, sir.
Yeah, good morning, you all. Honorable Dr. Mrinalini Fadnavis Madam, Vice Chancellor of Punyashlok Ahilya Devi Holkar, Solapur University, the chief guest of today's program. I welcome you, Madam, and I extend my sincere thanks for sparing your valuable time as the chief guest for this program.
Thank you.
The guest of honor for this today's program is Dr. B. Surendranath Reddy, who is professor and head of the School of Mathematical Sciences from SRTM University, Nanded. Sir, welcome you for this inaugural ceremony. Professor Nikam sir, who is head of the General Science Department, all head of the departments, various deans of various activities, all faculty members and your participants. The participants from other states and abroad, I welcome you all for this 1 week faculty development program on essential mathematics for engineers and researchers. Although SKN Sihagarh College of Engineering started in the year 2010, since inception of this college, the research is the most important element and component which we work together with all the faculty members. As in the beginning, we have 5 different UG programs at this college, and it was engineering UG programs. So from inception of this college, we have given strong motivation for the students to go for the project-based learning or experiential learning through various activities. And I'm so proud because every year we organize the different activities like project exhibitions, which is at the state level, and almost more than 300 projects are exhibited by our students of this college. Now, as we support for these innovations and the projects, the outcome of this all activities was the International Solar Vehicle Championship, which was organized in the 2017 by the students of this college. And specifically saying students of this college because the students are most important elements. If the students takes more interest, I think there's a great outcome which we have seen in the last 10 years at this UG level project competitions as well as innovations. The way students they have carried the International Solar Vehicle Championship in 2017 as well as 2018, it was really the wonderful outcome which we have seen. Because that it was not only the Solar Vehicle Championship. Because of these activities, there are few students, those who have become the entrepreneurs in the same field, in the solar field, and they are successfully running their enterprises in and around Pandharpur nowadays. Now, the FDP which we are organizing, the title of this FDP is Essential Mathematics for Engineers and Researchers. And this is the second activity because I remember before 5-6 years, we have organized the first similar kind of FDP, which was the softwares and mathematics for researchers and engineers. And as we are working very sincerely for the students, at the same time, we are working seriously for the faculty members. And I am proud to tell you that almost more than 30 faculty members today, they are pursuing the PhD from the various universities. And almost 15 faculty members, those are having already the PhD qualification and working in the capacity of associate and professor. In the 2017, we applied for the NAAC accreditation for these institutions. And I am proud to tell you that in the first cycle of the NAAC accreditation, we got the A grade. Now, doing this all, we feel that the encouragement and motivation given for the students and the faculty members is not enough. The continuous upgradation of the faculty members is very important because when the faculty members are upgraded, they are very helpful for the students. Now, today's program, FDP program, we are conducting on the 2 different platforms. We are using this Google Meet for few participants, and majority participants will be on the YouTube link. So, see, parallelly, we are having the YouTube and Google Meet link for this FDP program. Now, as our Vice Chancellor, Madam, she is chief guest for today's program, and as a majority of participants from the out of states and abroad also, I must mention that during this pandemic situation, the way our Vice Chancellor, Madam, has conducted all the activities, even the examination which was conducted by the university, I think 100% students, they have appeared for the examinations very successfully without a single problem. I must appreciate the efforts taken by the Madam. I know that this is not the platform, but as the participants from the other part of the country and abroad, they must know that how the Solapur University is functioning. As the Solapur University is the university which is only for the one district, but The way Madam has taken all the activities in this situation, it was really appreciable, and I must extend my sincere thanks to the Madam to spare the valuable time for today's program also. I will not take much of the time. Once again, I extend my sincere thanks to the Department of General Science and Mathematics for organizing this wonderful program, for the faculty members for upgradation of their knowledge in the field of mathematics. And I request all the participants to take the maximum benefits and to have the wonderful interaction, to have the wonderful queries to the resource persons. Once again, I welcome you all. Thank you very much.
Thank you, sir. I'm delighted to introduce guest of honor of today's program, Honorable Dr. V. Surendranath Reddy, the man of distinct vision and a fountain of illuminating ideas, an idol of knowledge and experience. Sir is working as an assistant professor at School of Mathematical Science of Swami Ramananda Tirth Marathwada University, Nanded. Sir has done his PhD from Hyderabad Central University under the guidance of Professor V. Suresh, the Bhatnagar awardee. His research area is algebra, analysis, and soft set theory. He has published 20 research papers with 36 citations. Under his guidance, 2 MPhil and 3 PhD have been awarded, and 5 are in queue. Sir has organized 3 FDP on ICT tools with 17,000 teachers participants and delivered more than 20 talks during COVID-19 pandemic. He also delivered 15 invited talks in various conferences, seminars, and workshops, and more than 30 lectures in UGC Net Set coaching scheme. I would request Sir to please enlighten us with his kind words of wisdom. So please.
Thank you, Madam.
Welcome, sir.
Honorable Vice Chancellor of Solapur University, Fadnavis Madam, respected Principal of this college, Kailash Karande Sir, Convener SV Pawar Sir, and all the dignitaries, teachers, research scholars, students who are virtually connected through this for this 1-week faculty development program. First of all, I would like to welcome all of you, because such type of programs are very, very necessary during this COVID. You might have seen so many different faculty programs, but this is definitely a specific related to mathematics or one subject. So it will be definitely interesting and fruitful for all this 1 week. I hope you all enjoy. When Karande sir is introduced about his college, I'm very happy to know that at the first attempt itself, they got A grade by NAC accreditation. So congratulations, sir. That shows your efforts and commitment, not only that, and a proper vision. Then, as a inaugural one function, because mathematics, anyhow, after this immediately I am going to talk a little bit about mathematics. So in this inaugural function, why such programs are so useful, I am one of the best example you can take me, because during when I joined here and about to take a research student, I was thinking about what topics I can take, because I am also new, and doing research or giving a topic to research student is not at all easy. So when I was thinking that what type of topics I can give to research students, then UGC has in 2013 or 14 this one. So UGC has released some list of selected major projects in mathematics. UGC released selected major projects in mathematics, and most of the time they have rejected only around 10% they have selected. So I thought, what about those 10% of the titles? Let's see those titles, whether anything is useful for us. So when I was going through the titles of that whatever selected on around 100 pages, then I found that there is one title, something like zero divisor graph. So first time I have heard about that, and then I thought it is something related to mathematics, I mean algebra as well as graphs. So let me see what is this. So I have searched things, and I came to know, and I have learned things, and I have given topic to one of my PhD student, and now he is about to submit his thesis. We have done a good work. May not be extremely good, but we have done a good work. And the most interesting thing is that the person who got that major project, recently he cited my research work. So that way I have given him back. I have found title. Then I worked with my students. We have published. Our work is cited by that person. That is a thing. So you can see that even here Solapur University, so one of my research student recently awarded, Tenge Madam. She worked on soft sets. That also same way coincident when I went to Aurangabad University, I was talking to one of the faculty whether you are doing PhD or not. He said, I am thinking to do research. Then I asked what topic you are selecting. He said something like soft set and rough set. Before that, I was not knowing. Then just because he told me, I started because I was in initial stage. So I also require different topics. So I thought I will see what is this soft set and rough set and all. She successfully completed her PhD in good publications. So just a matter of a small hint can actually change many things. Your direction in research. And in these 7 days, definitely you will get chance to listen to some of the applications, some of the current research trends going on. So definitely it will be a, if you take it as a serious, not the sake of just attendance, if you can really involve and attend lectures, surely you will get benefit. And in that way, I congratulate Seagate College for organizing such a wonderful topic. Mainly, I would like to suggest there may be many engineers and mathematicians here. So we should have a proper collaboration in the sense mathematicians should also know about some applications, explain to students so that they get interest. And the same way, engineers, they also should take some or understand some part of mathematics instead of just simply explaining this is the formula and you calculate it, you get result. So there should be a proper correlation between these two, then we get proper results. So I thank once again all of you for giving me this opportunity. Thank you, madam.
Thank you, sir, for your words of wisdom. We feel honored to have with us the Honorable Chief Guest, Her Excellency, Dr. Mrinalini Fadnavis Madam, Vice Chancellor of Punyashlok Ahilyadevi Holkar Solapur University, Solapur. I am profusely elated to take an opportunity to introduce her. Madam, you hardly need any introduction. You have made all of us proud of your distinguished work, your numerous capacities. Madam has completed 24 minor and major research projects. She has been appointed by the Governor of Maharashtra as subject expert on Vidarbha Development Board from November 2011. She has received research training patent in December 2015. Madam has 34 years of teaching as well as research experience. She has published 270 research papers at national and international level. She is the member of BUTR, RRC MOU, Nashik, and also she is a member of IGNOU. Madam has conducted 22 full-day program for women manager in higher education at Marathwada, Rajasthan, Maharashtra, Madhya Pradesh, and Chhattisgarh. 16 candidates awarded PhD under her guidance. She has published 19 books, more than 100 seminars and conferences attended in India and abroad at Russia, Japan, Canada, Australia, Zimbabwe, Bangladesh, etc. She has started 25 career-oriented programs. Apart from all this academic excellence, she has maintained her close link with her hobby, passion of painting. She has started oil painting 24 years back in 2008. She has created her interest in filament painting. The exhibition was organized at Rabindranath Tagore Art Gallery, Nagpur, Indore, Amravati, and Mumbai. 4 paintings are sold at China and 2 in America. She has received letter of intent for Punyashlok Ahilyadevi Holkar Solapur University Incubation Center at the hands of Honorable Governor and Chancellor Shri C. Vidyasagar Rao. She has established the School of Languages, Cosmetic Technology and School of Allied Health Science. She has introduced course in agrotourism and established agrotourism center in university. She has developed 35 skill development programs. She started research For researchers, she has started course and capacity building programs for women managers for first time in university. On behalf of the management, I thank her for providing her gracious presence to join us today to enhance our joy. Ladies and gentlemen, we rarely get this kind of opportunity to listen the words of a great knowledgeable speaker. I request Honorable Madam to please enlighten us by her thoughts. Please, Madam.
Thank you so much, madam. I am really happy to be part of this particular 7 days program on essential mathematics for engineers and researchers. The principal of the college, Dr. K.J. Karnade sir, similarly the resource person, Dr. B.S. Reddy sir, all the dignitaries from different places. As it has been said, it is from abroad also. So I welcome you all in the university as well as the college which is associated to our university. So with this note, I should say that the college who is working very hard for all such efforts, which is a need of the day. FDP is an essential thing, and you have to keep on updating all the issues which is related to the not only to the mathematics but all the subjects which is in your domain. I think the effort which you have been taken for this particular thing, I would like to congratulate Sir Karnad sir and all your staff members that you have taken a good initiative to start this particular program in the light of the new education policy. Because our new education policy is also innovative, dynamic, and it has been clearly stated that a lot of things has to be very creative and innovative, because the faculty should be trained first, and then the students, those who are from different domain disciplines, and they will be definitely very you can say the useful treat they will get out of such type of programs. So again, congratulations to all of you, because you have done a good work, and 7 days is a pretty good period where UGC is also saying human resource development areas, or now presently said as education ministry is also focusing on such type of development programs, and it should be a continuous process. It should not have a break every 6 months, every in a year you have to show that your teachers are being updated. If you see that any industry or any institution of a national repute or international repute, even if the person is retiring after 6 months, they will ask that person to attend such type of faculty development programs. So in 6 months, what the product or what the output that person can give to the institution, that is the botheration of the system where we have to work for the quality. And that's why definitely this is a good work on the basis of the quality, and you have also covered a good quantity of teachers, students, those who will be very happy to get different insights in the area of the mathematics. And mostly I will be very happy when the research work, you have mentioned the word research, so that is very important, because that is the need of the day. India is looking for such type of areas where we have to go for different type of research works. So this is really a proud moment for all of us. Now coming to this FDP, and when it is related to mathematics, when the students are there, even the foreigners are there, and our own natives are there, we are all aware that the two names in the mathematics are very important and renowned, that is Archimedes and Aryabhatta. So Archimedes is such a person which everyone knows that what contribution he has given for different type of issues which is related to the basics of the mathematics. Similarly, Aryabhatta is also very renowned person, and we are really happy that every Indian, when it moves out of India, we got a respect when it comes in terms of mathematics, engineering, or the research related work, or statistics also, or any area which is related to academics and industry. It is always says that you are a country from Aryabhatta. So it is a proud for us, because see, when we compare with other people of engineering section, our engineers are always ahead because the base or the root system has been developed in our country long back. Aryabhatta was a student of Nalanda University, and it has been said in the new education policy that we have to remake our system based upon the Nalanda and Takshashila universities. So I think mathematics is the base where we have to start on this, that how the country and states can be upgraded on this basis. Archimedes is also having the similar type of potential. When we are proud of India, naturally he is born in Sicily. So many people, those who belong to that area, Europe and Sicily, they are really proud of movement for them also, that they have been or rather they are working on such areas which is shown by them by the Archimedes. So these are the people, those who we need to understand how they have developed the mathematics and related areas. Basically, I would like to say there are various opportunities for mathematics as well, because both of them, Archimedes' father and Aryabhatta himself, was an astronomer also. And astronomy is also the base of the mathematics. And therefore, they are creators of mathematics, but they have also different dimensions on the area which has been, that time it has been touched. People have not aware about how the earth was, whether it is round or flat or it's square and all that. But they have given all the idea that how this notable invention of Archimedes and Aryabhatta, they have given the point that how all these things are important for the human life. And therefore, with their interventions and innovations, they have made proud movement in the field of mathematics, statistics, and all related areas. So I would like to say that students and teachers have a, you can say, platform or the potential they can develop, as Archimedes has also developed pulley design with the help of, or rather for the help of the sailors, that how the object can move up and down. Now it looks very ordinary because now we are using all these things, but these type of inventions are still necessary. And there's so many things which can be made with the help of methods of exhaustion, and that is the area of shapes. So there are still issues where we need to quantify, we need to understand the quality. The value of PI has also been taken care by both of the learned persons, and I think there is a still scope for the researchers to understand how the circles, cylindrical shapes, parabola, how we can use in a different patterns. That is the way I think we need to understand and move for the research work. Considering the Aryabhatta's contribution, that is a algebraic equation which he has developed, that is for the first degree of determining the value of pi, and the more important that the correct pi value up to the 4 decimal place. So you all know that, but how it is related to the different places. He has given the astronomy as one of his research area, and then it has been related to the religious rituals of our India. Is it not unique? Definitely, this is very unique, where we need to understand when we are moving in the system of pandemic. It has also some cycles. It has also some issues which is related to the astronomy. Many people are also calculating how this is working. Is it a total not related to the human thing, but it is also related to nature? And then when nature is related to the astronomy, we need to think about the very interesting issues which has been raised by our own Aryabhatta. So his contribution is based on 4 chapters. And I think this is the time when we are talking about the research, that all the students and teachers, when teachers will take initiative, as Reddy sir said, they can give the different topics for the students for the research work. I think we have to go back and to think how Nalanda professors were thinking on these lines of astronomy and all related issues, even various things which is related to nature. It is also based upon the mathematical calculations. So that type of research work can be the part of our system, and that thing has to be taken care with the help of the Aryabhatta's contribution. He has given 4 padas, that is 4 chapters we can say. One is Geetika. So that is based upon the planetary revolution during different issues of calculation of years, how the distance is from one place to another, how this the natural systems is working on the base of the calculation, which is based, the base is related to the mathematics. So this Gitika is part of the one of the chapter. Another part is Ganita. So Ganita is arithmetic and geometric progression. Simple, then quadratic, simultaneously intermediate equations. That are the things which is the part of the Ganita. And of course, you people know because that is the core part of the mathematics. Then Kala Kriya, that how you are calculating months, days, as I have already said, thing is happening, then it can be calculated how long it will be, what type of impressions it will have on the society. So mathematics is also part of the society religious things, which he has a vision that time. You can understand how visionary he was. So then Gola Pada, that is Gola chapter, that is also related to the geometry, trigonometry aspects. So these are the things which is related to the shape of the earth, day and night system, then zodiacal signs, horizon, what type of horizon things we need to study and understand. So these are the things which is very, very interesting, not only from the point of view of one particular subject, but it is a part of our social system as well. When we are thinking or talking about the research areas and relating mathematics with some social system, we need to understand how, like, I can give an example of how solar and lunar eclipse is having some mathematical base and how it is affecting the human system. Similarly, all these calculations, which is based upon the zero, square root, cube root, these programs have given a big contribution for the space programs, satellite calculations, and different type of impacts for the society. What we are doing, all these things, it is also based upon the satellite, and therefore these calculations are very, very important for the system as a society, as a researcher, or as a teacher. Last but not the least, I would like to say, now we are also working on the health science. And therefore, when we say, we always separate mathematics and health issues in a different way. But Ayurveda and other system, which is based upon the thing which has been told by Aryabhat, it is based upon our body structure. 7 chakras we have in our body, right from the head, Sahasrara, to Mooladhara. And that is also have a mathematics. How it has been set in the body, it has typical calculations, and how we do the work, what we eat, what we wear, how we behave. All it has a base of some calculations, which has been a blend of Ayurveda and mathematics. I think if you have thought on this, it is very good. But you have not thought on this, this is the part of the research we can come up, that how our the entire nature system, our body, is based upon the different activities and can be calculated with the help of mathematics. So there are n number of areas where we can definitely work a lot. And again, in 7 days, when you are getting different insights, that how this particular subject, the essentials of mathematics is, of course, the basic things you are going to understand, learn. You must be knowing something, then you're developing in a different way. But in a similar way, you are moving towards the research areas. That is more important. And I am really want to see how this type of programs can be useful for research. Some new ideas, if it is coming out, that will be welcome. We have already started in our university incubation center that is fully based upon the creativity and innovation. So I really feel that the principal of the college, they should take initiative, such type of ideas and creativities are coming. So you can enroll with us, and you are already the part of the university. So such type of activities will be the part and parcel of the incubation center, and that is the need of the day, which we have to take our university in a different heights. So again, I'm really thank you, and you have given us the opportunity to talk with your students and delegates. And really, again, would like to congratulate you for this wonderful program. Thank you so much.
Thank you so much, ma'am. Thank you so much for your influential message. We are charmed by your sharp fluency. Thank you so much. We are at the end of inaugural ceremony. The best and beautiful thing in the world cannot be seen or even touched. They must be felt by heart. Thank you is one such prayer among them. I consider it a great privilege to propose a vote of thanks to all the dignitaries who have witnessed it as a memorable and successful event. Today, my words are not enough to express the gratitude. On behalf of SKN Sinhagar College of Engineering, Koti Pandharpur, I would like to thank our chief guest, Dr. Mrinalini Fadnavis Madam, who graced us with her thought-provoking address, which set a perfect platform for our college. I would like to thank our principal sir for all words of wisdom that redirected a source of energy within us. We will ever remain grateful to you and we thank you for being with us today. I would like to thank Head of the Department of General Science and Engineering, Professor Anil Nikam, for his continuous support and motivation. My sincere thanks goes out to all resource persons, our institute deans, HODs, and faculty members who always stand by us, guide us, lead us, and motivate us. We feel proud and thank you for making us feel happy with your presence to this function. I express my sincere gratitude towards all Indian and foreign participants for showing their enthusiastic participation and interest. At the end, wishing you all beautiful moments, pleasant memories, and all the blessings a heart can know. Thank you all. Thank you so much. With the permission of dignitaries, I announce that the inaugural ceremony is over. Thank you so much.
Thank you.
Thank you. Thank you so much.
Thank you so much, ma'am. Thanks a lot. Thank you, sir. Thank you, sir. For participants, please be with us. We are starting our session very soon. The first session. Pawar sir, over to you.
Yes, ma'am. Yes, once again, I welcome you all for first session of FDP. Very shortly, we are going to start our first session. The speaker of first session, I will introduce him briefly. The speaker of first session is Dr. B. Surendra Reddy, sir. Currently, he is working as Assistant Professor, School of Mathematical Sciences, Swami Ramananda Tirtha Marathwada University in Nanded. He has completed his PhD from Hyderabad Central University in the year 2006 under the able guidance of Professor V. Suresh Bhatnagar Awardi. His main research area is algebra analysis and subset theory. He has published near about 20 research papers with 36 citations, 3 H index and 1 I-10 index. Under his able guidance, 2 MPhil and 3 PhD students have completed their respective degrees, and currently he is guiding 5 PhD students. Under his guidance, he has completed one minor project, Rajiv Gandhi Science and Technology Commission project on awareness and training on free open source mathematical software. He has coordinated online courses at SRTMU Nanded and PTMT 2015. He has organized 3 FDPs on ICT tools with near about 17,000 teachers participation and delivered more than 20 talks during COVID-19 pandemic. He's having few achievements. His main achievement, he has qualified CSIR GRF NET during 3rd semester of MSc. He has given 15 invited talks in conferences, seminar, or in workshops, delivered more than 30 lectures in UGC SETNET coaching scheme. He is an institutional NAC core committee member, qualified the HCU entrance for MSc admission in 2004, merit cum mean scholarship holder during MSc. So we have very renowned resource person we have for the first session. Now I would like to request Professor Reddy to begin with his session. Thank you.
Thank you, sir. Thank you for your introduction. Am I audible?
Yes, sir, you are audible.
Yes. So let me share my screen. My lecture will be part of some presentation and part of just like class lecturing, because mathematics doesn't make much sense if we don't write it right. So I will be sharing both. Okay, so today my topic is actually, first of all, I would like to thank again Pawar sir, because during this last 6 months, I have given several lectures, demonstrations, but not on mathematics other than my regular online courses to my MSc students. So I'm very happy with uh, delivering some mathematics related lectures, and I hope I will deliver soon more than ICT. Of course, ICT was required at that time, so I have devoted much time for that. So today, because the title of this FDP is Essential Mathematics for Engineers and Researchers. So I thought, and not only this, most of the time, being mathematician or mathematics teachers, we are not aware of many applications. That is maybe one reason students get lost interest. Only theorem proof. So what is the use of this one? Is there any applications in real life? So many such things ask anyone. Many people don't understand the importance of mathematics. So I thought in this 1.5 hour or whatever time it may be, I'll try to cover some application which is actually very interesting, and there are so many such applications. If as a teacher, if we just give some time and explain to students about such applications, not in detail, and ask them to do as a project, because many times UG or PG level students may want to do some project as a compulsory one. So instead of doing something a normal one, if we can give such projects, students get interest, and they also can work when they go for research and so on. So there are so many applications, especially when it connected to linear algebra, and there are so many applications when it comes to number theory. So today I will be discussing some application mainly called Google PageRank. So many of you might be knowing, if you just go and search, for example, if I say here Google PageRank, then you can see here about within just 0.6 seconds, this many results Google has displayed, and by priority, whatever it is displayed, we may wonder how it is doing here. By typing some keywords, how fast this Google search engine is able to show these many results. You can see that how many web pages are there, and in this web, more than 796 billion. Okay, 796 billion results are there, when a million maybe. So how we can find useful information which is required for us, because it is not at all possible we go through it each and everything and find out. So what Google is doing, they do most of the work for us, and they will try to show the websites which are highly ranked. So whatever ranked first will be displayed here, whatever ranked next one will be displayed next to this, and so on. Okay. So you may wonder what is mathematics behind this one. Definitely there is a mathematics behind this, and lot of applications, heavy mathematics actually is used. So I will try to cover some part of mathematics, what is behind this one, and one application like how this Google PageRank works with 1 or 2 examples. Okay. So before starting this, I would like to say that this I have learned on my own, with of course references from books and YouTube videos, from web using Google search. Okay. So I would like to thank all of them. I would like to acknowledge their work. For example, there is a book. There are a number of books on Google PageRank and beyond itself. So one of the book which I have referred is this There is a reference you can find out. It is about 235 pages, and each and everything they have given. For example, introduction to web search engines, what is meant by crawling, indexing, and query processing. Then ranking, what are all different ranking web pages search engines are available. Then this one entire chapter is for mathematics of Google's PageRank. Okay. Then whatever other things are there, each and everything is very interesting. It is just like a novel, one can read it. It's a nice thing. And the other one paper which I have taken some of inputs is by the Google Spectrum by Varun Iyer. It is also a nice article. Many things he have explained excellent. Then there is also one another article which I have followed. You can also search the mathematics of Google search. If you type it PageRank algorithm, the mathematics of Google search, from this Cornell website, you will find one of his lecture. It is also very insightful, and most of the time it gives better information. Okay. Then I also have taken some information, some inputs from a book, namely one of the section power method for approximating eigenvalues. So whoever engineers, whoever teaching for engineering mathematics, they may be knowing this power method, but we'll see how powerful it is in this such a technological world. Okay. And now, of course, my presentation. So based on those inputs and my understanding, I have prepared some presentation, and I will be explaining some results. First thing is, I may be wrong at some places. You are most welcome to correct me. I am ready to learn, and I am not saying that I will stop learning, or whatever I say it is correct and you just follow it. Okay. So keep in that mind, I am a learner, so there may be so many mistakes also. If you can correct me, I am happy to learn. Right. So I'll just introduce what is this Google PageRank algorithm. Then what is the mathematics behind this algorithm. Then we'll discuss those results quickly. Then we'll come back to that with an example. Okay. So we go here and there. Fine. So I hope you can see my screen, right? Hello.
Yes.
You can see my screen, right?
Yes.
Yes, sir. Yes. And also one request to all teacher participants, students, research scholars. If you have any difficulty or you want to interact with me in between, you can always stop and ask me. It should be, I always encourage my lecture should be two-way. Okay. Whenever you have a doubt or whenever you have a suggestion, you can stop me and give it. We will take that and then we go ahead. Okay. So be attentive first thing. Just don't put it your video and mic off and work some other things. Okay. Try to follow things so that you may understand something better than me. What this Google PageRank is all about. We all know that we are in this technological world, and internet has become our integral part in education, learning, or whatever things we are doing it. Okay. So whatever we want to find some information, we simply immediately go to some search engine, example Google, Bingo, or Yahoo, whatever. Many people may use different search engines, and just type something, just like I've shown you before. I typed Google PageRank and it shown the lot of information with n number of websites. Okay. Then you may be as actually thinking that how efficient, whatever the result it is shown as a first one, second one, third one, how important it is whether I get maximum information from that or not. Okay. So the Google what follows is algorithm namely called Google PageRank. Maybe they may be recently have some modifications to this, but basic version is the following. Okay. So this PageRank algorithm was developed by these two people, Larry Page and Serge Brin, when they are postdoctoral students at Stanford University. So because of this person, they have given this PageRank, even though that page also matches with whatever techniques they are using it. Okay. So in 1998, they have come across, I mean, they have start using this PageRank algorithm for their search, Google search. Okay. And it has become the most popular one within short time. The what main idea is the idea that the information on the web, they will going to put it in hierarchy, okay, by means of link. For example, it is just like their motivation when I read somewhere is that just like a bibliographic metric, citations in research papers. If we see it, then some people have too many citations. How they got citations? Or we say that somebody's research is very good if they have a good number of citations. Okay, that means because when I am working on some problem, I give some citation, I give some reference to that person that this work is done by this fellow. That means I am referring some person. So the more and more people refer a particular person, that person value increases. Okay, that same idea they have taken from here. So more if I go to some web page, there some other web page is link is given. Okay, that means that website is given importance to that particular website. Okay, so that particular website get more rank than other website. Okay, so that means here the hierarchy is mainly based on this linking the popularity. Of course, linking the popularity among all keywords, whatever we are searching. And not only that, if I just link to some website which doesn't make much sense, then also you don't get search. Okay, so they also keep in mind that the importance of a page, not only the number of links, but the most important thing is the importance of that page, whatever they have linked to that website. Okay, suppose I have my own website and I have given so many links which are not relevant. So even you give, that website is not going to get a better rank. This is in general and it makes more sense. So assume that I am recommending. Okay, so if I want to recommend, first of all, I should be in good enough, and I should not recommend so many people, because if I recommend one person, for example, for MTTS or any other mathematics training program, then if I recommend one person or maximum two persons, my weightage will be considered there. Suppose if I recommend in my class there are 30 people are there, just all 30 people I start recommending, then there is no value for my recommendation. So that also plays one important role here. So how many websites you recommend to others and how much important those web pages. This is the main idea about this Google search they have thought of. Why this is so interesting, in 2002, when this Google PageRank was starting, at that time, this one of the MATLAB founder, Clive Moller, he stated that this Google PageRank is the world's largest matrix computation. The order of that matrix is 2.7 billion at that time. Okay, that means in their whatever thing they are having, usually they do it in the form of matrix. So the size of the matrix is 2.7 billion. So you can understand how complex it is and how they are getting results within seconds, right? Now by this time, we have Google searches more than this also past recent. So 30 trillion web pages Google searches and more than 100 billion times a month, and these numbers are keep on increasing. Okay, because every day people are getting connection to internet, they are getting access to internet, so people start searching more and more, and people creating websites more and more. So the more websites starts increasing, their complexity increases. Okay, fine. So what usually this any Google search, not only Google search, most of the search engines, what they do is basically there will be three things. The first thing is they crawl, that means they closely observe all the websites available publicly. Okay, so they will try to find what are all the websites available publicly, and they will give indexing for those such websites with the help of using some keywords and phrases. Suppose just like if I search Google PageRank, then they will try to find all the websites which have this information with these keywords. Then they will try to give indexing for those web pages, so that just like call it page 1, page 2, and later they can access it with the help of those indexing. And the final important last one is that when we search this one, assume that we have collected some, this search engine found around 10,000 websites. So among those 10,000 websites, the most important thing is how we can give the hierarchy, which is the best, and then which is next, and so on. And that is the most important why Google has succeeded. Okay, there are so many search engines. You try to search the same 3 keywords from Google and from Yahoo and from Bing, you will see that the order of hierarchy whichever display is usually different. Some may match, some may doesn't match. That is mainly because of their algorithm technique they use. So here they are going to use that out of those 10,000 websites, they will start giving hierarchies 1, 2, 3, and so on, and it will be displayed as it is. And most of the time, most information we get it from first 10, 15 websites. And there may be some websites whose rank is less, but maybe some good information is available. Okay? Because these are all approximation, calculated by approximated. Sometimes we may lose some website information also, right? Fine. Now, we just understood roughly about this Google PageRank. Then what is the mathematics behind here? How mathematics played some important role in this one is the one theorem called Perrin-Frobenius theorem. What it says is that if A is a positive column stochastic matrix, then the largest eigenvalue is 1 and all other eigenvalues have their absolute values less than 1. Okay, and such eigenvalue we will define now is called a dominant eigenvalue. So if our given matrix is a positive and matrix, then the largest eigenvalue one can get is 1. Okay, and not only that, this is the eigenvalue 1 is of multiplicity 1. So whatever eigenvector we are getting, it is unique up to scalar multiplicity. Okay, and for this eigenvalue, there exists a, you can call it unique eigenvector, whose, if you take those values in that vector, then sum of its entries should be equal to 1. So this is very, very useful, and mathematically this is very, very useful in many applications. Okay, because in real life situations, most of the time we get this positive matrix, because whatever entries we are going to get, they're not negative entries. And most of the time, I'll explain what is meant by column stochastic matrix. So even though there are some conditions, most of our applications actually fit into this type of matrices. Okay, so then we can find, we can take the help of this one, and eigenvalues plays very, very important role, eigenvalues and eigenvectors. Then there is also another most important one, in the sense this power method convergence theorem is played an important role in this Google PageRank. What this theorem says, that if A is an n by n diagonalizable matrix with a dominant eigenvalue, this, what is meant by dominant eigenvalue, that is the largest eigenvalue available. Okay, then whenever you have a diagonalizable matrix with dominant eigenvalue, then there exists a non-zero vector x naught, such that you take these iterations a x naught, then a square x naught, a x naught, and so on. This sequence converges to a eigenvector, dominant eigenvector, or of course some scalar time a dominant vector. Okay, these are the two results which played a crucial role in this Google PageRank algorithm. And of course, this power method has n number of applications, because this power method works whenever you have a diagonalizable matrix and whenever you have a dominant eigenvalue. And when we can get a dominant eigenvalue, this Perrin-Frobenius theorem says whenever you have such matrix, it gives that such required eigenvalue. Okay, so today I am discussing only one, maybe one application, but this power method has n number of applications. Will the you can find out because it gives the best way to calculate some approximation, eigenvalues approximation or eigenvectors. Okay, without doing huge calculations. So in that sense, this power method is very, very useful. Okay, so before going to this, whatever how this Google page look like and so on, we see these two theorems and whatever result are required for mathematics. Then we will go back to that one. Is that okay? Right, because as a mathematics teacher, we always like to have first some mathematics, rigorous mathematics, then we will go to the applications part and so on. Okay. Any doubts Or you have any problem so far? Okay. So we go through some yes. So let me define some basic things quickly. Then so some basic things we define. Okay. First thing, you take many things related to matrices we will define. So take A, which is a square matrix. And we say that if you take any real number, suppose you call it lambda is R, we say that lambda belongs to R is called an eigenvalue for this A if, what is the definition? If there exists a non-zero vector, okay, you can call it belongs to n Rn, such that this A, when multiplied with this vector x, it should be same as lambda x. Okay. Then we call this lambda as eigenvalue, and this x is called eigenvector corresponding to this eigenvalue lambda. Okay. Now, if you observe this one, Ax is equal to lambda x. So if x is an eigenvector, then any scalar times is also an eigenvector. Why? Suppose if I multiply by some c, then you can see that a times cx, c is some constant. Okay, obviously it is same as c times ax because it's a scalar, and this ax is lambda x. Okay, so you can write this as lambda times cx. Okay, so that shows that if c is any constant and x is an eigenvector corresponding to lambda, then cx is also eigenvector corresponding to lambda. So if we have one eigenvector, then any scalar multiple is also an eigenvector. So we have a freedom to select this suitable eigenvector by taking suitable constant. Okay, fine. Now, what is meant by dominant? What is meant by dominant eigenvalue or dominant eigenvector? Okay. So this dominant name itself suggests it should dominate each and every other eigenvalue. So basically, if A is an n by n matrix, and say suppose lambda 1, lambda 2 up to lambda n, these are all eigenvectors. Okay. Then eigenvalues. These are all different eigenvalues. Then say suppose some lambda I, okay, is called dominant eigenvalue if you take the absolute values, this one should be strictly bigger than any other absolute value. Okay, so that means here for every j, okay, not equal to I. Take for example, say when we say lambda 1 is a dominant eigenvalue if the absolute value of lambda 1 is strictly bigger than remaining all lambda 2, lambda 3 up to lambda 8. Then we call it this lambda I, we call dominant eigenvalue. And the xi, if you call it, which is the corresponding xi, the corresponding eigenvalue is called dominant eigenvector corresponding to this dominant eigenvalue lambda. Okay. So it is not necessary that every matrix has dominant eigenvalue. For example, if you take, obviously you can take simply an identity matrix. Okay. What are the eigenvalues for this one? Obviously, what are the eigenvalues for this matrix? At least some people can respond, right? Instead of one person keep on saying.
1 and 1.
Very good, 1 and 1. So at least help me sometime so that I won't get bored. Yes. So obviously lambda 1 is 1 and lambda 2 is also 1. So can we say that one lambda 1 is a dominant eigenvalue here?
Yes.
No, we cannot say it. Why? Because what we require here is strictly bigger than. Okay. So this matrix does not have a dominant eigenvalue. If I take another matrix, suppose if I call it just to see that you people get eigenvalues easily, I have taken a diagonal matrix. Okay. Obviously, what are the eigenvalues? So 1, 2, 3, right? And which is the dominant eigenvalue? Is 3, right? Okay. So if at all it is like this, instead of this one, if it is like this, then whether we have a dominant eigenvalue? Instead of 1, 2, 3, if I have 2, 2 and 3, whether this matrix has a dominant eigenvalue?
Yes. 3.
Yes, 3.
Yes,
So yes. So what you observe here is that whatever the largest one, okay, that should be the unique one. If you have more than that, then that cannot be a dominant eigenvalue. Okay, right. Fine. Now, what we do here is, see, suppose you assume that you have a, say, 3 by 3 matrix. Okay. If you have a 3 by 3 matrix, then you can obviously find all eigenvalues by solving that third degree equation, right? If you have some 4 by 4 or some smaller one things, you can try to find eigenvalues with a little bit of work. Okay. But whereas if you have n, where n is sufficiently large, n is say 100, 500, whatever it may be. Just like Google page, it is n is some 8 billion, right? So can we find eigenvalues? Is it possible? It is a huge task. It is not at all possible to find. So what we can do is, can we find at least approximate, because most of the time real life problems, they don't require exact solutions. Approximate solutions are more than sufficient. Okay. So approximate eigenvalues. So there may be many ways where one can find some eigenvalues, how we can get approximate things. Whoever know about numerical methods or numerical analysis, they know it. So one of the method which we are going to discuss today is this power method. Okay. So this power method is useful when to find this approximate eigenvalues and eigenvectors. Okay. So what we require for this is that you require that matrix should have a dominant or eigenvalue. Okay. So if you have a dominant eigenvalue, then what this power method says is that you take A, which is n by n matrix. Okay. You take n however large it may be, no problem. Then you take some x naught, which is the some initial approximation. Initial approximation to whatever we are going to have this dominant eigenvector. So I will simply write dv just to understand dominant eigenvector of this E. Okay. Now, how we do this? How we can find some approximately, even though we may not able to find exactly the dominant eigenvector, we'll try to find the approximately close to that. Okay. So for that, you take x1, which is simply A x naught. So given a matrix A and this x naught, which is initially approximation, we can select it suitably. Then find this A x naught, which is not at all difficult because this is a n by n matrix and this is a vector. Okay. So we are actually just like multiplying a vector to a matrix. That is somewhat easier than multiplying two vectors. Then the second iteration, you find this A x1, which is same as A times x1 is our A naught. So therefore, this is A square x naught. Right? You keep doing this. So suppose that xk, this is nothing but A xk minus 1, which is same as if you substitute backwards and so on, what you get here is ak x naught. Okay. So what we are getting here is xk is equal to ak x naught. Okay. Now this power method says that after some, by taking k sufficiently large, this ak x naught will be very, very close to that required dominant eigenvector. Okay. Now one may ask, what is the guarantee that such k exists so that is very, very close to what we require? Okay. So for k large, this whatever ak x naught, this you can approximate with dominant eigenvector. Of course, dominant eigenvector are some multiple of scalar multiple of that dominant eigenvector. Okay. For this power theorem or this convergence theorem for power method gives guarantee that such k we can actually have. Okay. So we just go to the important theorem, which says that you can call it this as convergence of the power method. Okay. Fine. So whether can anybody tell this statement roughly, at least if not detailed? At least can somebody roughly say what is this convergence of this power method? No answers. We should involve, right? As I said, I am learning, and you may be knowing better than me, and many of you are engineering teachers here. Huh? Yes. Yes. Roughly, what this convergence theorem says? What this convergence theorem says is that if A is an n by n square matrix which is diagonalizable, so we can quickly recall what is meant by a diagonalizable matrix. If there exists an invertible matrix P and a diagonal matrix D, such that if you can write this as PD P inverse. Okay, then if we can factor our A in this form, then we can call it that matrix as diagonalizable matrix. Okay. Fine. So take such matrix, and if this has A has dominant eigenvalue, okay, or eigenvector, whatever you call it. At this case, if these two conditions are satisfied, then there exists a non-zero vector, you can call it x naught, such that when you consider the sequence, this ax naught, then a square x naught, a cube x naught, and so on, ak x naught. This sequence, if you consider they are vectors, they actually converge to approximately, they converge to the I can call it some scalar times So some I can call it some C times dominant eigenvector. Okay, so this sequence actually converges to a dominant eigenvector which we require. Okay, so we can actually, what this theorem says is that, because most of the time we state the statement and we'll prove it and we don't know what is the significance of this and so. So in general, for real life applications, this dominant eigenvector plays crucial role. In the sense, our result, whatever we are going to find, it actually relies on this dominant eigenvector. Okay, so it is all about finding the dominant eigenvector. So how we find this dominant eigenvector is how we can guarantee that it is because of this statement, convergence theorem. It says that when you take this sequence, that means if you start doing this, you will get, after some iterations, you will get whatever required, at least approximately. Okay, up to some error which is negligible. Now, why this is named, of course, as a power method, you can see that this a x naught, a square x naught, a cube x naught, and so on. So you are repeating these things. And remember, we are not actually calculating a square, a cube, a power k, and then we are multiplying with x naught. What we are doing actually is this one. Okay, because multiplying two huge matrices is not at all the easy one. Okay, but whereas multiplying a matrix with a vector, that is fine. Okay, so what we are actually doing here is this: x1, you multiply a with x naught, then x2, actually we are not multiplying a square and then x naught. We are actually multiplying whatever we got for x1, we are multiplying a to that. That means it is iteration process. The moment we get, you take with the initial vector, then multiply by a, whatever vector you get, for that you multiply again by a, and so on. Okay, and whoever know about algorithms and all, you will see that this makes a lot of difference between multiplying a power k and then with x. Okay, so this proof, it is not at all difficult. We can simply I can just say, I can outline this one and how this works. What is the where we are using this diagonalizable and dominant eigenvalue. Okay, fine. So this a is assumed, it is given to be diagonalizable, because until unless as a mathematician we prove something, we are not happy. We'll go to application, that example only after just proving this one or two small results. It is not at all difficult. Okay, so we know one result. This a is a diagonalizable, and whenever it is diagonalizable, it has n distinct eigenvectors. That result you can easily do it. It is not a problem. So call it x1, x2 up to xn. They are all different eigenvectors. Okay, corresponding to eigenvalues lambda 1, lambda 2 up to lambda n. Okay, these are all eigenvalues. Now, because this matrix has a dominant eigenvalue, then without loss of generality or renaming, we will assume that lambda 1 itself is a dominant eigenvalue. Okay, so if that is not the case, you just rename them and you bring it the first one. That's all, that's nothing else. So without loss of generality, assume that lambda 1 is dominant eigenvalue, and of course x1 is the corresponding dominant eigenvector. Okay, so this is the x1, which is dominant eigenvector. Okay, fine. Now, because you have this independent, this x1, x2, xn, they are independent because they are different and they are independent eigenvectors, and A is a matrix of size n by n. So we know that this x1, x2, xn. So this x1, x2 up to xn, they form a basis. So here linear algebra is coming into picture. They form a basis for this Rn. So what is meant by quickly a basis? They are linearly independent, and any element of this Rn can be written as a finite linear combination of this xi's. Okay, fine. Now you start with any x naught, okay, which is non-zero, because now x naught belongs to Rn, you can write this x naught as linear combination of these xn's. Okay, so there exists C1 constant, C2 up to Cn, such that your x naught can be written as C1 x1 plus C2 x2 plus and so on Cn xn. Okay, so while selecting this x naught, we have to make sure that this C1, whatever we are considering, is non-zero, and that is always possible because there are a number of ways to select that. We can select our x naught is our initial approximation, so we have to make sure that while selecting our C naught, you take C1 is non-zero. Okay, that means this x1 component should present in that. If C1 is 0, then this x1 won't be there. So we require, when we are taking x naught, we require that in such a way that x1 is there in that. Okay, so that we can get the required result. Right now, if we take a, that means if we multiply a from left side both sides, what we get here is ax naught. Then C1 I can bring outside. This is same as ax1. Similarly, ax2 plus and so on Cn axn. Right? But what is our ax size? Because of this, our ax size is nothing but this lambda I. You can call it some other this lambda I xi. Right? So in place of this axi, if we substitute, what you get here is C1 in place of ax1, you get lambda 1 x1 plus and so on Cn lambda n xn. This is your ax naught. Okay, that we have called it as x1. Right? Then again multiply by a to x1, which is ax1. That is same as a square x naught. This again by taking a inside, what you will get here is C1, because this lambda 1 and ax1, which is again so lambda 1 square x1 plus and so on Cn lambda n square xn. Right? Okay. So if you keep repeating this one at kth stage, suppose this ak x naught, which you can call it as a xk minus 1 or a xk plus xk minus 1. Okay. This is nothing but akx naught, which is equal to what you have here is C1 lambda 1 power k x1 plus Cn lambda n power k xn. Okay, I hope there is no problem. It is a very basic calculation. Now what we do is, because these are all lambda 1 is non-zero and so on, you can take lambda 1 power k common. So what you have here is C1 x1 plus the second one is C2 lambda 2 power k you have. So this is same as lambda 2 by lambda 1 whole power k plus and so on. What you have here is Cn lambda n upon lambda 1 whole power k, okay, into xn. I hope no one have any objection up to here. Now we use little analysis. What we know about, because this lambda 1 is dominant eigenvalue, that means the absolute value of lambda 1 is strictly bigger than each and every lambda I, right? So we can, while doing itself, we can, while giving this name and all lambda 1, lambda 2, lambda n, we can again make sure that this is the process. Okay, that means after that there may be equal also, it's not a problem. So we can assume this is not at all a problem. Okay, because lambda 1 is a dominant eigenvalue, we know that this is strictly bigger than each and every other, but if necessary we can put it in this order, there is no problem. But what you observe is that because lambda 1 is strictly bigger than lambda I for every I not equal to 2, if you, what can you say about modulus of lambda I by lambda 1? That means this implies modulus of lambda I upon lambda 1 is strictly less than 1 for all I not equal to. Okay, so if you call it, this is just like some x. So what we have here is, so you can recall, if mod x is less than 1, Okay, then what we know is that for sufficiently large n, x power n tends to 0. Okay, right? So that means now if we apply that here, lambda 2 upon lambda 1 upon k, as k is sufficiently large, that means as k tends to infinity, this term tends to 0 and all other terms tends to 0. So therefore, if we use that result, and what you got here is that ak x naught. So whatever we have here, ak x naught, okay, this is converged. ak x naught converges lambda 1 over k, because remaining all terms are 0. Okay, they tends to 0. Fine. Any doubt here? So if you see this one, whatever we have here, this is actually because our x1, so I can write simply this as some alpha times x1, where alpha is some scalar. Because x1 is a dominant eigenvector, so what we have shown is that ak x naught actually converges to some scalar times x1, right? Where x1 is a dominant eigenvector, and that is what we want to show, some scalar times dominant eigenvector. We show that this sequence converges, right? Any problem? This is a very simple proof and interesting. One should know it instead of just only simply using it. Okay, fine. So what this theorem, when we can use this theorem, that is most important. If at all your matrix is diagonalizable and it has a dominant eigenvalue, then definitely with finitely many iterations, we achieve what we require, mainly finding dominant eigenvector. Okay. Now we simply give another result, which is also very, very useful, which gives guarantee of existence of dominant eigenvalue. Okay, dominant eigenvalue, and that is nothing but the theorem is, which I already stated, is Perron-Frobenius theorem. Okay, you can write here. Okay, so what is this Perron-Frobenius theorem says is that under some conditions, if you have a matrix, then it has a dominant eigenvalue and some other properties. What are those conditions we require is that if you take A is a positive column stochastic, positive and column stochastic matrix. So if A is our positive matrix, which is a column stochastic, then I'll explain what is meant by column stochastic. But let me state this. Then what we have here is, whenever you have a column stochastic, say, of course, this is one version of Perron-Frobenius theorem. We can generalize this to better values. Okay, that means so what I am stating here, which is the version which is useful for Google PageRank. Okay. So what it says is that the dominant eigenvalue. So in this case, so dominant eigenvalue is 1. So for all such matrices, the 1 is the dominant eigenvalue, and with multiplicity 1. That means you can call it simple eigenvalue. So it eigenvector doesn't repeat up to some constant, they are same. Up to isomorphism, if you consider, then except constant multiple, there is only one eigenvector corresponding to this. Okay, and this there exists, you can find a x naught, whatever it may be, such that you have a you can find a dominant, you can find this dominant eigenvector by suitably multiplying that scalar. What it says is that such that the sum of those values, whatever you have in that vi, is equal to 1. Okay. Yes. So this is Perron-Frobenius theorem. One version, as I said. What is a column stochastic matrix, and what is a definition? You can quickly say it. What is meant by column stochastic matrix. So this says that your column vectors are nothing but actually probability vectors. So what is meaning of saying this? The entries should be non-negative. So each and every entry, whatever you are calling at those matrix, if you call it A, Aij, so each Aij should be equal to greater than or equal to 0, and sum of this Aij in each column, okay, should be equal to 1. That means when you sum the value entries in the column, that value should be equal to 1. So for example, just if you take this one, obviously it is an example of stochastic matrix. Okay, this is a column stochastic matrix. If I take 1 by 2, half, then 0, 1, this is also an example of stochastic matrix. So what you should remember here is that when you try to add each column, that value should be equal to 1. Such matrices are called column stochastic matrix. Of course, the same thing you can use it for row stochastic matrix also. That is self-explanatory. If you add each row, the value of some of the entries in each row should be equal to 1. Then we say it is row stochastic matrix. Okay, fine. Now you can. It is not at all difficult to show that this, if A is a positive column stochastic matrix, then this dominant eigenvalue 1 is the dominant eigenvalue. We will show that 1 is obviously for a column stochastic matrix. 1 is always an eigenvalue. Why 1 is always an eigenvalue? That means A times, you have to find some V such that A times V and our lambda is 1. So we want to show that A times V is same as V because our lambda is 1. Okay. And this is not at all difficult because of this column stochastic. We know that A and A transpose, they both have same eigenvalues. So we show that A transpose times V is equal to V for some V. Therefore, 1 will become 1 is the eigenvalue of A transpose. So therefore, it is the eigenvalue of A also. Can you see why? What is our V? What should be our V we can take for a column stochastic matrix? For example, you take this 1 by 2, 1 by 2, 0, 1. Okay. So that transpose will become this. So which is obviously row stochastic matrix. So what element I multiply, what a vector I take here so that I get same V here. This rows has some advantage whose sum is equal to 1. So obviously if I take this is 1 and 1 here, then what I get here is 1 and 1. Okay. So obviously if you take E for any n, 1, 1, 1 and so on 1, then what you get here is A transpose E is same as E. That means that is our V. Okay. So that shows that this column vector containing all entries as 1, okay, is eigenvector. Okay, E is an eigenvector for A transpose and hence for A, and this corresponds to what? Because it is 1 times E, so therefore it corresponds to eigenvalue lambda is equal to 1. Okay, so I hope there is not at all difficult one here. That, and you can also easily show that this 1 is actually a dominant eigenvalue. Okay, that means if you take if lambda is any eigenvalue, okay, if lambda is greater than 1, then we get some contradiction by using that A. Okay, you take there exists some V such that this AV is lambda V. Okay, then by simplifying this, you get a contradiction by using convex combination concept. Okay. So you can use this, right? So that I'll skip. You can take it as an exercise and you can show it. Okay, show that this 1, whatever we are getting actually is dominant eigenvector, eigenvalue. Okay, fine. So why this result is so useful? So whenever we have a positive column stochastic matrix, then this theorem guarantees that there exists a dominant eigenvalue, namely 1, and not only that, it is unique. That means multiplicity 1. Up to scalar times, there is only one eigenvector, which is, and that will be the most of the time our resultant eigenvector, okay, which we require. Fine. With this little mathematics, now we will be again go back to our application. Now how we effectively we use that thing, we will see it. Right. Now let me explain little bit about how this Google PageRank, how they thought, okay, how they come up with this algorithm. Then I will show some examples and we will calculate. So basically, what is this? Their main idea is rank of page I, okay, is sum of rank of that page. This is I, anything is sum of ranks of pj, where pj is linked to pi. That means if you go to pj, that particular, suppose say page 2 or web browser, some one, they have given link to page 1. Okay, so rank of pi is sum of ranks of pj, where pj is linked to pi, hyperlink. Okay, so just take small example. Suppose assume that you have A, B, C, okay, and D. These 4 are web pages. This is very interesting. Try to listen at least. So assume that I will just randomly give some links. So A is linked to B, okay, and A is also linked to C, right? Our first simple step we, okay. B is linked to C, and C is linked to D, okay, and D is linked to A. Now, if at all we want to find rank of A, rank of the page A, so obviously what we have to find, and also suppose I will write here, just instead of this I will take this, okay. So first we should know, to find the rank of A, what are all websites they are mapping to, they are giving link to that particular website A. So here what are the websites, pages which are linked to A? So this D is 1 and C is 1, okay. So this D and C are given links to website of A. So rank of A is calculated based on rank of D plus rank of C. This is the simplest one, but if I make a small adjustment, because C is mapping or C is giving link to only website A, no other website, okay. So if at all I make some small change, suppose assume that C is also mapping to B. So this is what I said about recommendation. So this C is recommending 2 websites. Earlier C is recommending only one website. Now it is recommending 2 websites, namely A and B. So therefore, rank of A in this case is rank of D plus, is it rank of C or something else? Because C is referring to A as well as referring to B, entire rank of C don't go to rank of A. What you get here is rank of C by 2. Is this step clear? Because just like I am recommending 2 persons, so obviously my priority, half priority will go to A and half priority will go to B if there is no bias, right? Okay. If at all, so if I take C and if C is also referring to D, then in that case, what is rank of A? Is rank of D, okay? Because C and D are referring to A, but C is referring also few more websites, so that is rank of C. Okay, is this clear? Any problem? So how these ranks are usually calculated is with this basic rank of A is equal to rank of D. That means first of all we want to find here D and C. they are referring to A. Now we have to see whether D and C are also referring to any other website or not. If they are not referring, then entire rank of D and entire rank of C will go to rank of A. But if at all they are referring to some other websites, they are also referring to some other websites, then rank will be split. It will be their entire rank you won't get it. That means entire is credit you won't get it. The entire recommendation you won't get it. Just like that. Okay. Is that clear? That is the basic thing which it started and it will go. Yep. Yes. Now, so what they did here is basically you denote PIs. They are nothing but pages. Okay, web pages. P1, P2, P3 and so on. Page 1, page 2, page 3. Then the rank of PageRank, you can call it PageRank. PageRank of PI, initially they defined those two, Larry Page and the other guy, they have defined basically using the same idea by generalizing that summation rank of PJ. Okay. What we have considered here, we have not considered, for example, B in this picture. Why? Because B is not referring to A. So when we calculate rank of A, this rank of B is irrelevant, not necessary. So when you calculate rank of a particular page, what you require is what are all different pages are there which are mapping to, okay, which are referring to A. So that we call it as some, this PJ belongs to that set. Suppose you call it BPI. So what is this BPI? Set of pages, okay, linked to the particular page IPI. Okay, and this much is not, because if at all that same PJ is referring to more than just like in example. So what we want to see here is this. What is this cardinality of PJ means? This represents number of pages PJ refers. Suppose if PJ is referring just like here, our C is referring to 3 different pages. So therefore here you got 3 here. Okay. So that is the general formula here. And this is the basic they started for Google PageRank, how they have calculated. So let me write here how the Google PageRank is calculated. Initially they started with this formula that I'll write GPR. So just to say Google PageRank of any page I is summation GPR, Google PageRank of R PJ, that is PJ. Okay, PJ upon how many, this PJ is how many websites it is referring. Okay, this summation over PJ over that set of all belongs to referring to PI. Okay, now let's have a small example and calculate this. What you observe here, we want to calculate a page rank of a particular page, but this involves the page rank of another page, which how we will find, right? So there is a difficulty here that this formula has unknown values. Just like you want to find a factorial and you are defining again in terms of factorial and right hand side. That makes, whether it makes sense? Huh? So to overcome this, what they did first thing is, to overcome this, they have given initial page rank to all PIs. That means the first step, they have given some page rank at initially to all websites equally. So that equalness, if you have n websites, obviously 1 by n. Okay, that means the first stage, every page has, so assume that we have searched something and found some n websites. So first thing what they give is, for each n website, the page rank is same, namely 1 by n. Okay. Then in recursive way, we will calculate page rank again and again, and we go through it, and at some stage we will stop, and that is the actual page rank of all the pages. Okay. So what is our initial vector? So our vector is nothing but page ranks. Okay. So our initial vector is 1 by n, 1 by n, 1 by n. This is initial page rank vector, and our idea is to find the exact page rank of these web pages. Okay, fine. Now what we have to do for this, you calculate now. That means rank of p r0, I will write r0 just to mention rank. So rank of pi at first stage, which we know what is that, is equal to 1 by n. Then how we will calculate rank at first stage, that means second stage? Now we know this. We will define this in terms of previous page rank. That means here we will write summation this rank at initial stage upon pj by this cardinality of pj. Now at next stage, that means of next iteration, we will find rank of each page is based on previous one. That means here. Okay. This is pj, sorry. Are you understanding what we are doing? Then and so on, we will repeat rk. That means page rank at kth iteration is summation rank of that pj at k minus 1 iteration upon this page. Okay. And if you see this one, this has similarities with our power method. So this has similarities with whatever we have used for power method. What power method we did? We have taken some initial approximation x naught, then we have calculated ax naught, and whatever we got based on this, we calculated again ax1, and right. Fine. So this is the how this first initially started. Now let me take one quick example and calculate those values, and then we go to this. So suppose take this example. Can you see this example? Can you see this example?
Yes, sir. Yes, sir.
Yes. So let me put side by side. Try to understand. At least here you try to involve, and if you are not understanding, you please ask. Okay. Can you see my both screens? One side image.
Yes, sir.
Yes. So that I can write properly. Okay. Now I'll write here. So take this picture. So what we have here is, we have 4 websites, web pages. Okay. Now page 1. Web page 1 is referring to which web pages? So you can call it, if it is referring, it is outlink, and somebody is referring to 1, it is. So I will write outlinks, and I will also write inlinks. Okay. I'll write here for page 1, then page 2, page 3, page 4. Okay. Yes. Now can somebody tell what are all the outlinks P1 has? That means from page 1, which websites we can able to go? We can go to page 2 and page 3 and also page 4. That means this page 1 is actually referring to each and every fellow. Is this clear? Now what about inlinks? How many people are referring to page 1?
4 only. 4 only.
Which one? 3 and
3, 4.
3, 4. Yes, very good. Now, when it comes to page 2, what about page 2 quickly? 2 is referring to 2 websites, 3 and
4.
4. What about who are all referring to page 2 in links? 1 is referring, is the only one, right?
1.
Is this clear? Yes. Now, what about P3? That means page 3. What are all outlinks? 3 is referring to 1.
1.
Only 1, right? And inlinks, that means what are all 3 is receiving? 1 is referring, 2 is also referring, 4 is also referring.
And 4.
Right? Okay.
Yes.
Yes. Now, what about P4? Page 4. Outlinks is
Referring 1.
it is referring
1.
to 1 and
1.
3 also it is referring, right?
1, 3.
It is referring to 3 also. What about inlinks? 4.
1.
We are receiving
2.
from 1, also receiving from 2.
2.
Right?
1, 2.
Now, with this information, can you see that which is the better page rank? Is it possible to calculate? At least first guess it, then we will see. Huh? Outlinks are just like I am recommending. Okay, that P1, page 1 is recommending is nothing but outlinks. Inlinks means somebody is recommending that particular page.
P3.
P3. Huh?
Yes,
that page 3.
Yes.
Why?
Because many
Because
are recommending our website.
Everybody is saying that this person is very good, and that particular person is saying that no, actually page 1 is better, right? This candidate is better. He is giving entire his full credit to that one particular person. Okay. Whereas page 2 is some people are referring, but 3 and 4 he is referring, but only very few people are referring to that particular person, right? So just like whoever having more citations, usually they have more credit and so on, right? Oh. Now, so for this problem, we will first apply that initial this result, whatever we have discussed. Okay, what is that result we have discussed? This one. Then we will convert into matrix and see. So first initial stage is what? What are the page ranks? Initial page ranks. For each page, equal page ranks we have given, right? What is that? For each stage, we have given the initial first stage we have given 1 by n, 1 by n, 1 by n. Okay, that means each page rank has now first stage has equal value. So I can write here first iteration. So iteration 0 I will write I0. Okay, so I0, what is P1, P2, P3 and P4? What are the ranks? We are calculating ranks here. So first time it is 1 by 4 because there are 4 websites. Is this clear? Yes.
Yes.
Now tell me I1, that means after first iteration, what is the formula? Find out first of all what are all things which are referring to P1. They are required. Is this clear? So 3 and 4 are recommending this fellow. Is this clear? 3 and 4 are recommending. You can see here what we have written here. This, what is this PJ represents? They are all pages linked to page 1, right? So what we get here, so I'll write it here. So rank 1 of page at first stage, rank of P1 is rank of P2 because this, what is this? P3 is referring, right? Upon something plus rank of P4 upon something. So rank of P3 upon what is the denominator? Here I have to write RG, previous iteration, right? So P3 is referring which websites? What are all P3 is referring? How many P3 has? Is referring to only 1, right? So therefore here by 1 we'll get. And what about P4? What are all it referring? 2 websites, right? 1 and 3. So what you get here is this. Is this clear? But at initially, what is the value of R0 of P3? All are same. So this is 1 by 4 plus 1 by 4 upon 2. This is 1 by 8. Is this clear? So this is namely 3 upon 8, right? So we get here value 3 upon 8. Similarly, you can calculate what is at first stage iteration 1, what is rank of P2 How you will calculate rank of P2? What are all in links are available? Only one is up coming, right? So that summation you won't get anything. Okay. So if you simplify that, then you get ranks and so on, and you can go to next stage, and so on. So the page ranks will change. Now earlier it is 1/4. Now the page rank after first iteration rank of page is 3/8. Okay. Is that clear? Which is better than whatever previous earlier one has. And if you go to next iteration, it may change, right? So we keep on doing this until we get some better approximation. Okay, fine. But if you observe here, there are only 4. If you have suppose 10, then this summation may involve more and more values. So instead of going through this summation process, what we do is we represent in matrix representation. So instead of going to this summation one, what we do is we represent matrix representation of this formula. Whatever formula we have, the same thing, but we represent in the form of matrix. Okay. So what is that? Is called, we will call it, this is hyperlink matrix. So this is, you can call it some Hij. Obviously, what should be this matrix? This value is 1 upon, because this 1, it is not actually value 1, it is 1 upon the value of the cardinality of Pj, where Pj is linking to Pi. Okay. If there is no link, then the value is 0 otherwise. So is this hyperlink matrix, whatever I have explained, is this clear? Hij is 1 upon cardinality of Pj if Pj is referring to that particular Pi. Okay. So just quickly write this. What is this Hij will look like? Here you can write, you can see that this matrix H, you can call it. Okay. So this H is a obviously 3/3 matrix. So this row 1. So here if you want to write, what are all pages referring to? So this is H11, right? So let me write here H11, H12, H13, H21, H22, H23, H31, H32, H33. Okay. So what is H11 says? The H11 says that whether P1 is referring to P1. Obviously we don't have. So this diagonal entries are 0 right now, right? Because we are not referring to self website. Now, what is H12 represents? What is meant by H12? So this value will be 0 if P2 is not referring to P1. So let's go back to this picture and see whether P2 is referring to P1 or not. The website 2 is not referring to 1. Only 1 is referring to 2. So what value we get here? We get value here 0. Is that clear? We get value 0 here because 2 is not linking to 1. What about 3? Whether 3 is linked to 1? 3 website is linked to 1. Yes. So at that time, what value we get? How many websites 3 is referring? So 3 is referring to only 1, right? So what you get here is 1 here. Okay. Right. Similarly, H21 you can find, and you can start writing what is H21. Whether 2 is linked to 1 is the question. So whether 2 is linked to 1, it is not. So whether I did any mistake there. What is this? Whether 1 is linked to 2 or not, that is the question. Now whether 1 is linked to 2, yes. So now how many 1 has outlinks? This is referring to 1, 2, 3. So here what you get here is 1/3. Similarly, you can fill the values and you get a matrix. Okay, and that is the matrix which we have shown here. This is 1/3 value, 1/2 value, and so on. Okay. Then how we are doing iterations by taking the approximation. So I can explain through this picture now. We are taking the initial approximation 1/n, 1/n, 1/n. So that is our V. Here n is 1/4. So 0.25, 0.25, 0.25. Then whatever that formula is, actually basically you can check that it is nothing but AV. Okay. So when you calculate, what you get is 0.37, 0.8, 0.33, 0.2. So what it says is that means here, so whatever we are having here, this is the page ranks after first iteration. Earlier, what is the first initial recommendations? Page ranks each have same 0.25. But after first stage, the page 1 got 0.37, 0.8, 0.33, 0.20. So after first stage, page 1 has better ranking. Then you repeat again, second time. Then if you see here, this is the after calculation, what you are getting here is 0.35, 0.14, 0.29 and so on. So if you keep on repeating, you observe last these two. So A7V we got 0.38 and A8V also we got same. So that means after any iteration, can you mute yourself, please? Some noise is coming. Yes, thank you. So what you can see here is, let me close this, the values. Yeah. So after 7th iteration, you are getting same matrix. That means there is no change. So that itself says that this is what we required. This is the dominant we required. So this 0.38, 0.12, 0.29 and 0.19. So this will be considered as the page ranks, final page ranks of those 4 websites. So as we discussed earlier, in this example, at least we have guessed that this page 1 will be the better one because 3 and 4 are referring and page 3, yes. So what we had earlier is page 3 and page 1, right? In this calculation, which one we got? We got that page 1 has the highest ranking, then page 3 has the highest ranking. Now let's go back to see that picture. Why this is true? Why that is true? Because page 1, why page 1 is superior than page 3? Why we think that? According to that calculations. Because page 3, if you see, then he is referring to one person and 3 people are referring. Okay. Whereas here 2 people are referring, but most important people are referring here. See, 3 and 4 both are referring page 1. Okay. Whereas page 3, 1, 2, 4 are referring, but 2 is not so considered. Right. So in that is the reason we got that this page 1 has more value than page 3. Okay. Yes. Fine. So what we got here is that if you simplify this in the form, what we are getting, this page rank. So where is this one? So here itself I can write in the matrix form. So whatever we are going to get, I can call it this H we have denoted, right? So this how we can write. So each page 1, page 2, that is considered as a vector. So HK, okay, of X naught is our HK minus 1. How we are writing here is HK of X naught and so on. That is HK minus 1 of H of X naught and so on. So this is what we require and we have written that here. Okay. Fine. Now let's quickly go to, there is a small modification is required for this one because take this example. So if you go to next example, you have A, B, C, D, 4 things. If you see this D is not referring to anybody else. That means, suppose I started with A, website A, then from website A I searched to gone to website D. But after I reach website D, I cannot go back to any other because this has no in links inside that. That means it has no outlinks inside D. So I cannot go again to some other website if once I reach D. Such nodes are called dangling nodes. So this D is a dangling node, and you can observe that whatever we are having here, that entire column is 0, 0, 0, 0. Obviously, because this D has no outlinks for any website A, B, C, right? So they have, when they designed that H, they got a problem with this one, that there may be possible that some website does not have any links to other websites. Okay, it has only in links, it does not have outlinks. So such nodes are called dangling nodes. So to overcome that, what they did is, it is very simple logic. Once somebody receive this D, then just like initial approximation, after receiving this D, that person can go back to any other website with equal probability, or we can say equal voting. So this column is replaced by 1 by n, 1 by n, 1 by n, 1 by n. That is 1 by 4, 1 by 4, 1 by 4. So that make more sense. So whenever you arise this dangling nodes, then define that value instead of 0, you define that value as 1 by n. And that is the new modification to that hyperlink matrix. This already it is there. Extra what we are doing here is, if at all it is a dangling node, we are putting as 1 by n value. Okay. So therefore that matrix, whatever we earlier we have here, that is now become 1 by 4, 1 by 4, 1 by 4, 1 by 4. Now, remember, you can observe that this is not a stochastic matrix because some of those last column value is not 1. Whereas here, we have made it to stochastic matrix. So again, we can go with that power method and we can have continuous iterations, and after some time we get a result. This is the second modification. Okay. Then after these iterations, we got this matrix. I'll skip that. And there is one more problem they have faced. That problem is that even though some website has a link, but it is just like repeating, like something like cycling. For example, take this G. So if I consider this G, if I come from A, I can reach to D and then I can come to G. But there is no way I can go from G to A or G to B or G to D, C. What it will do is, from G, I will go to F, or I will come to H, then I will again come to G. So there is a cycle is there. Okay. So once you go by mistake, you go to this G, you will be only revolving around only few websites. You are not able to go to other websites. Okay. So this is the third problem they have faced it. Even though it is not a dangling node, but these nodes or these web pages are in such a way that they keep going inside again and again within only limited websites. Okay. So that is also a problem. So to overcome this problem, they have added some more thing. That is, once they receive to this G, then from this G, they will define new value. From this website, they will define a new value to any website, equal distribution. Okay. So that's why. So what is the meaning of saying that? I'll write it here, and that concludes that final one. So finally, what we are doing. So initially we had a hyperlink matrix. So we have observed that sometimes it need not be stochastic. That means there may exist dangling nodes. Okay. So to overcome dangling nodes, we have defined what is called something called S, which is coming from H. So obviously H plus whatever that column having zeros, we are putting 1 by n, 1 by n, and so on. So don't assume that this is in proper way. We are only putting that inside that H, we are putting such column. If there are more than 2 columns which entries are 0, then put all those entries in this way. Then this, we have seen that it is a stochastic matrix. Okay. Now this second problem arises is that even though it is a stochastic matrix, just like we have seen here, even though this is a stochastic matrix, once it reaches to some place, you will be revolving around only few websites. So at that time, what they did is, finally they defined a Google matrix G, which is combination of S and there is something called, you can call it E. This is called you can call it teleport matrix. Okay. And this, of course, S is called the stochastic matrix. what is meant by this teleport? This name itself suggests that from there I am going randomly to any my website. I may visit to any other website once I reach to this place. Okay, but to give the better rating, they have used a called damping factor, call it alpha, and here 1 minus alpha. So they have taken the convex combination of, this is your Google matrix. This is the Google matrix, which is convex combination. So this alpha is of course between 0 and 1. Convex combination of this S and E. S is the actual matrix, of course, with one modification. And E, it is the teleport matrix. What is that teleport matrix? If you want to write by 1 by n here. Okay. Or you write this. This E is all entries having, so you remove this and you put it here, all entries with 1 by n. Okay, that means even I can go to same page also. From page 1, wherever I was there, I may search randomly that same page again also. So 1 by n, diagonal entries are not 0 here. So this is your E. So therefore, what is your final page rank calculation? How it goes is this Google matrix is alpha times S plus 1 minus alpha times E. That is, you can simply write in this way. And this maybe many people might have seen, and we have derived it with some understanding. And what is this alpha is called a damping factor, and usually Google takes this alpha as 0.85. Okay, and this make more sense because this alpha into S is here. So most of the time we want a genuine, I mean he is surfing through genuine links, not some arbitrary links. So that's why here alpha is taken in this way. And 1 minus alpha times means it is 0.15 here, right? Here it is 0.85 times S plus. Okay. So of course we can change this alpha. We can take 2 alpha is equal to 0.5 or alpha is equal to 0.6. There is no problem, but they have guessed it here. And with this alpha is equal to 0.85, within however big matrix it may be, within 50 to 100 iterations. So with alpha is equal to 0.85, however big matrix it may be, with 50 to 100 iterations, they get the result, required approximation result. After that, the values are not going to change much. So that resultant ranking we can give. Okay, fine. Whether any doubts so far here? A long session, more than 1.5 hours to closely 2 hours. Now you say, I am sure not everybody might have understood completely or even half. As I said, there are number of books are written in on the Google PageRank itself. So it may not be possible for you to understand in one lecture itself, but with this motivation, if you go and read things, you will understand more things clear. Okay. This is the matrix which I have explained it, and this is the calculation one can do it, and one can find very easily. This damping factor is 0.85, and whatever example we have considered here, for that we got this many iterations, and they are very, very close. Hello?
Sir.
Yes. So I think I concluded from my end.
Okay.
I'll give some references. You can share with them later.
Yes, sir.
Whoever interested, they can go through it and they can explore. There's a Google PageRank. Usually I give to my MSc students. They try to learn something. And just like this power method, where in power method we try to multiply powers, and there is also another interesting application that is called SVD, singular value decomposition. So that is in singular value decomposition, you decompose your matrix into three important matrices. Using that, you will give some ratings. So maybe many people may be knowing about Netflix. Nowadays, Netflix has become famous even in India because of this COVID. So what Netflix was done in 2006, that interesting story I can tell. They have announced some $1 million prize for improving their rating system. So they have a rating system in their Netflix. So they want to give better rating for previous based on the users. Okay, so based on whoever watched some movies, based on that they get some reviews, and that they try to rent it. Okay, so they have announced a worldwide contest. One can search just Netflix prize. Then many people have participated. It is a huge contest, very famous. So what they have, whoever participated in that, they got better results than whatever earlier having algorithm. And what they used is the singular value decomposition. So they have used singular value decomposition. Using that singular value decomposition, they have eliminated the noise. That means whatever movie ratings are very, very less, they have removed that, and they got some good number of things based on that they have calculated. Okay. So that also one can see it. And there are n number of applications based on projections. If you know projections very well, then least square, there are other things which one can see it. Okay.
Okay, sir. I will share all the things with all participants.
Yes.
Santosh, sir.
Sir, I have a urgent meeting. So
just a few questions. If somebody have any question, Santosh sir, please ask questions.
Yes, sir. Yes, sir. One question is there. Sir, how to choose X0 in power method? Is it unique X0 in power method?
No. There may be actually infinitely many things will be there. Only you have to select that X, whatever you are, if you know about, you select something which is not orthogonal to that vector. Okay. See, there will be very few vectors which is orthogonal, right? If you take a vector, okay, x1 is given. X1 is what? Your dominant eigenvector. Okay. So we have to select x0 which involves that x1. So if you go through that power method in detail, you can select your x0 in such a way that anything you select, if it is not perpendicular to your x1, then that will work. So it is not unique. There will be too many initial approximation you can start with. So select any x0 which is not orthogonal to your given x1, then that you can write it linear combination which involves your x1 also.
Okay, sir. Okay, sir.
One more is there. I think exact meaning of eigenvalue in real life. One participant has asked this question. What is meant by eigenvalues?
Okay. So what it saying is that you take a matrix. See, matrix is just like take some rotation in your two-dimensional thing. You take a rotation. Okay, that rotation by 90 degrees. Okay. That you can represent in the form of a matrix. So take that rotation, and so for example 90 degrees. Okay, so you take any vector and try to rotate to 90 degrees or whatever that rotation we have defined. That is your a times x. Okay, then can it be equal to some lambda times x? That means is it parallel to the x? Because lambda times x is as a vector, it is either when you multiply it, lambda times x, if you see graphically, either it is a stretch or contraction. I mean, it is an extension or a contraction. If you can get by that applying that matrix, then we say that whatever value lambda we are doing it, that we will call it as a eigenvalue. Okay. So after applying that matrix whatever matrix, desired matrix is there, when you apply that to the given vector, if you get similarity to that vector, then we can call it whatever scalar lambda we are applying to that. That is an eigenvalue.
Okay, sir. One more question, sir.
Yes, sir. Yes.
Sir, Perron-Frobenius in theorem, Perron-Frobenius theorem.
Yes. Yes.
There is statement is if A is a positive column stochastic matrix, then dominant eigenvalue is 1 with multiplicity 1. I think it is a contradiction to the definition of dominant eigenvalue. Am I correct?
No. See, what is meant by multiplicity 1 means whatever corresponding eigenvector you are getting.
Okay, sir.
The corresponding eigenvector is only 1 up to multiplicity.
Okay.
See, what is meant by dominant eigenvalue? That value should be the bigger one. Okay. So here lambda 1 is your value 1. Now find x1, which is the eigenvector corresponding to that lambda 1. That vector, whatever we are getting, that and any other eigenvector if you have for 1, they are scalar multiple of 1 and the other. That means you have only multiplicity 1. You don't have two independent eigenvectors which are eigenvectors corresponding to the value 1. That is the meaning.
Okay, sir. Got it, sir.
Yes. So usually in a dominant, if you have a dominant eigenvalue, okay, it may be possible that you may have more than 2 eigenvectors corresponding to that one. Here, multiplicity 1 means you have only one eigenvector corresponding to that eigenvalue. By maximum, you will have scalar multiple. That means dimension is 1. That is the reason.
Thank you, sir.
Well, I think questions are over. Now we're at the end of session. On the behalf of SKN Srinagar College of Engineering, Pandharpur, I'm very much thankful to Dr. B. Surendranath Reddy for his valuable and excellent presentation. I hope all the participants, you may get new idea about the applications of linear algebra to the power methods and other things. Thank you so much, sir, for your time and valuable session.
Thank you, sir. Thank you all for listening patiently.
Yes.
I hope you can definitely you start exploring. You will understand things far better. Okay.
Yes. And one announcement to all the participants. Next session we will begin with 3 p.m. sharp. So please join before 3 p.m. with the same link. Link will be same for all the sessions throughout the Google Meet link will be same for all the sessions. And YouTube link will be provided before the start of session every day. Okay. So with this, I'm concluding session number 1. Thank you all. We'll meet at 3 p.m. today.